This is the screencast for section 4.3, example 6. We're going to look at some population growth using data and analyze that using calculus. See, the table 4.2 shows the population of Alaska in each 10-year census between 1920 and 2000. So 1920 is 20 years since 1900, 2000 is 100 years since 1900. Let's see. Part A asks us to find the logistic regression for the data. Now that's something that we've done in the past, so I'm not going to show you that on the calculator. I basically, though, did put these guys into L1, the years since 1900, and then in L2 I put the population. And then I went to second calc, Then I went to stat, arrow to the right to calc, and I did a logistic regression down here, number or alpha B. And then I picked list 1 and list 2, and I stored it into Y1, and then I've got my equation, which is this, 895,597 over, well, you can see it. And then my X min, here's my window that I set up, and then I've got this. So I graphed the curve, the logistic growth, over the data points that I had plotted, and it does fit very well, so that's good. Part B, use the regression equation to predict the Alaskan population in the 2020 census. So 2020 would be 120 years after the year 1900, so it's definitely going to be above 626,932. So I'm guessing somewhere in the sevens, maybe mid sevens. So I plugged in 120 into the logistic regression that I have here, and I got 781,253.18 people, which I said it was going to be mid. There's a little bit higher than mid, 700,000s. Again, that was just a prediction, so there you go. Part C, find the inflection point of the regression equation. What significance does the inflection point have in terms of population growth? So to find the inflection point, I did the first derivative of my logistic regression in Y2. Then in Y3, I did the derivative of what was in Y2. So my calculator is like first calculating Y2, the first derivative, and then in Y3 calculating the second derivative. It's going to plot this very slowly. And then I had to find a window, also very slow. But here you go, there it is. Good luck trying to find that on your own. It did take me a few minutes to figure that all out. So the inflection point occurred at 82.76 years. That's where the second derivative was 0. So significantly, what does that mean? Well, the inflection point is where the second derivative changes from positive to negative. So where the first derivative, the change in population, changed from increasing to decreasing. So really at that inflection point, it's like a maximum of the velocity, the population's velocity. So we found the year where the population was growing the fastest. It's a maximum of the velocity graph. So the maximum velocity was in 1982. And we could plug that into the first derivative. We could plug in 82.76 to the first derivative to find out what it was, what that rate of growth was. But it doesn't ask me to do that, so I'm not going to do it. Part D. What does the regression equation indicate about the population of Alaska in the long run? Well, in the long run, remember this is logistic growth, so we have that limit to growth. So basically the limit to growth is 895,597.80. So basically it's saying our population will never get higher than that. Then now try problem number 31, asks us for pretty much the same kind of stuff. Again, I'm not going to do this in my calculator in front of you. I'm just going to go through and explain it. So table 4.3 here shows the population of Pennsylvania in each 10-year census between 1830 and 1950, which is weird. So these are the years since 1820. So they're calling 1830 year 10, and I think that's just to get it off the y-axis so you can see where that data point is. So that's fine. So I put years since 1820 into L1, and then populations in thousands into L2. So I did the same thing I did before and just went to stat, arrow to the right to calc, and then logistic, because that's a logistic regression. Stored it into Y1, and here is the equation I got. So there is the logistic regression for the data. And of course I plotted it to make sure that the regression did fit the data points pretty accurately. That was part B. It asked me to do it anyway. C, use the regression equation to predict the Pennsylvania population in the 2000 census. Well, the 2000 census is going to be 180 years after 1820. So I had to plug in 180 years. And then, see, now, if this were me, I would have called this years since 1800 just to make life easier and made the first data point 20 and then 30 and then 40, but whatever. Anyway, so I plugged in 180 to the logistic regression equation, and I got 12,209.87. So that will be the population in the 2000 census. Now, I know what you're thinking. Pennsylvania only has 12,000 people in it. That's a huge state. No, remember, this is in thousands. So it's actually 12,209,000. So this is thousands of people, which means that it's really 12209,870 people. So we're looking at 12 million people, which makes more sense. Part D, in what year was the Pennsylvania population growing the fastest? So now, in the last question, they asked us to find the inflection point and tell what it means. We're looking at where the population is growing the fastest. So where it is changing the fastest, a maximum in the velocity. So a maximum in the velocity is going to be found by an inflection point. So that's what I did. Again, I told the calculator to find the first derivative in y2 and then the second derivative in y3. Now I know what you're thinking, Miss Larson, I could have just found a maximum of y2, second calc max. This is calculus. You've got to use calculus to get to your answer. And yes, you used one derivative, but they want you to take it that step further and understand that your second derivative is going to find your maximums in your first derivative. So I found the inflection point at 0.40 years. Then the second part of this question says, what significant behavior does the graph of the regression equation exhibit at that point? So that's, okay, what significant behavior does the graph of the regression equation? The regression equation is this, and from what we learned before, the fastest growing population there is going to be at that inflection point. So the graph of the regression is exhibiting an inflection point at that spot. Part E, what does the regression equation indicate about the population of Pennsylvania in the long run? Well, the regression equation, back up to Y here, has a limit to growth of 12,655, and remember that's thousands of people. So it's telling us that the population will never really get above 12,655,180 people, according to this regression.